As years pass by, the number of people and products needed to be moved from place to place around the globe is increasing. As passengers and consumers, we want everything to run smoothly. Whether we are booking flights, traveling to work, or wanting food readily available at supermarkets. However, businesses moving people and products around is a bit complicated and an expensive matter. This is where mathematics applies in the real world. Today, I am going to talk about transportation problem. Transportation problem is a special type of linear programming. So first, let us talk about linear programming. What is linear programming? The goal of linear programming is to maximize and minimize quantities such as cost, profit, production, and storage capacity subject to certain constraints. So what is transportation problem? It is concerned with determining the optimal strategy for distributing commodity from a group of supply centers called sources to various receiving centers called destinations in such a way as to minimize total distribution cost. Each source is able to supply a fixed number of units of the product called capacity, and each destination has a fixed demand called requirement. But how do we solve a transportation problem? Let me show you how. There are 4 steps in solving a transportation problem. Formulate the problem and set it up in matrix form. Obtain the initial feasible solution. Test the initial solution for optimality. Update the solution. Let's use this example. A company has factory A, B, C, which supplies supermarkets X, Y, Z. Daily factory capacities are 35, 40, and 40 units respectively. Daily supermarket demands are 45, 50, and 20 units respectively. Units shipping cost is shown below. Determine the optimal distribution for the company to minimize shipping cost. First step is to set up and formulate the problem. Shown in the table are the different sources and its supply. Next, we have the different destinations and its demand. In this table, shown are the costs for transporting an item. Don't get confused. The 35 in the supply is not equal to AX plus AY plus AZ because the two are independent from each other. Our supply and demand have the same sum, which is 115, making the transportation problem balanced. In balanced transportation problem, all units that can be supplied are used to meet the demand. Unbalanced transportation problem occurs when the supply is not equal with the demand. If total supply exceeds total demand, a dummy destination whose demand is equal to the difference between total supply and demand is created. Similarly, if total supply is less than total demand, a dummy source of supply equals to the excess of demand over supply is used. All units shipping costs into a dummy destination or out of a dummy source is 0. Next, we have the initial feasible solution. In this presentation, we have least cost method, northwest corner rule, and VAM. Unfortunately, due to time constraints, we are only going to discuss least cost method and northwest corner rule. In least cost method, we are going to start by selecting the tile with the least cost, which is 5. If there are 2 identical values, you can select any of the 2. I am going to use AX. Since 35 is less than 45, I am going to input 35 in the table. Next, we are going to select the next least value. In our case, it is going to be the other 5. The limit of the supply is 40 and the demand is 45. Since we already have 35 in the previous cell, we are going to subtract 45 to 35, which is 10. Here are the next values, and here is the finished table. We're going to compute for the minimum distribution cost. We're going to multiply units shipped by per unit cost, and the sum of all the products would be 1,465. Next is the northwest corner rule. Start by selecting the cell in the northwest corner of the table. Assign the maximum amount to the cell that is allowable based on supply and demand constraints. I am going to input 35. Because we already have 35 on the first, we are going to subtract 45 by 35. The difference would be 10. Since we already have 10 on the first column, we are going to subtract 40 by 10. The difference would be 30. Because we already have 30 on the second column, we are going to subtract 50 by 30. The difference would be 20. Then we will get 20. We are going to compute for the distribution cost, and we will get 1,675. Optimality test. In this presentation, we have stepping stone method and UV method. Unfortunately, we are only going to discuss stepping stone method. We are going to use the table earlier. First, select an unused square. Next, trace a closed path from the selected unused square and back to it. We are only allowed to trace a path with used squares. Place an alternating plus and minus signs on each corner. Calculate for the improvement index for AY route, and we will get -5. Repeat for other remaining improvement indices. Next is AZ, and here is the closed path that it formed. Again, we are only allowed to trace paths with used squares. Calculate for the improvement index for AZ, and we will get -9. Next is BZ, and here is the closed path that it formed. 20 minus 30 plus 8 minus 12 is -14. Then we have CX, and this is the closed path that it formed. 5 minus 8 plus 30 minus 20 is 7. We are going to select the index with the least value. In this case, it is BZ with a value of -14. Update the solution. Since BZ has the least value, a cost saving might be attained by making use of BZ route. The value can be found by selecting the smallest number found in the squares containing minus signs. In this case, it is 20. This number is added to all squares on the closed path with plus signs and subtracted from all squares on the path with minus signs to obtain a new solution. Take note, do not touch the other squares. 30 minus 20 is 10. 20 plus 20 is 40. 20 minus 20 is 0. The solution is as follows. We are going to compute for the value of the shipping cost for this solution. Take note of the value for least cost method and northwest corner rule earlier. We are going to multiply 35 by 5, 10 by 20, 10 by 30, 20 by 20, 40 by 8, and the sum would be 1,395. It is less than initial feasible solution, which means we are on the right track. But take note, this solution may or may not be the optimal solution. We are going to test the improvement index for each square, and we are able to get the following values. The solution is not yet optimal because AY had a negative value. We are going to update the solution again by utilizing AY. The value can be found by selecting the smallest number found in the squares containing minus signs. In this case, it is 10. This number is added to all squares with plus signs and subtracted from all squares with minus signs to obtain a new solution. The new solution is as follows. We are going to solve the improvement index for the unused squares. First is AZ. 10 minus 5 plus 20 minus 20 is 5. Next is BY. 30 minus 10 plus 5 minus 20 is 5. Next is CX. 5 minus 5 plus 10 minus 8 is 2. Last is CZ. 5 minus 8 plus 10 minus 5 plus 20 minus 20 is 9. All improvement index is greater than 0. We are going to compute for the shipping cost. We are going to multiply 25 by 5, 10 by 10, 20 by 20, 20 by 20, 40 by 8, and the sum would be 1,345, which is less than 1,395 from earlier. Note, rule on the number of shipping routes being used must be observed. The number of occupied square in any solution must be equal to the number of rows plus the number of columns minus 1. 3 plus 3 minus 1 is 5. If the rule is not met, the solution is said to be degenerate. Degeneracy occurs when there are too few shipping routes being used, making it impossible to trace a circuit for each unused square. you have reached the optimal solution. In this video, we learned the transportation problem is a special type of linear programming. Each source is able to supply a fixed number of units of the product called capacity, and each destination has a fixed demand called requirement. The steps in solving a transportation problem. Types of transportation problem. Different ways of finding initial feasible solution. And 2 optimality tests. I hope that you learned something from this video and realize how mathematics is used in the real world. Thank you.